Hi, Michael Hansen here. This is a little different video than you usually see from me. You usually see me standing in front of my whiteboard and talking about, well, all sort of things. But since I wanted to present to you my presentation from my Master Thesis defense, and I don't have a projector or anything like that at my home, the only real solution was to record the screen of my laptop, and then I will explain what you see. This presentation is a little different than the presentation I presented at my Master Thesis defense. First of all, because my Master Thesis defense had to be restricted to 30 minutes, whereas here I can talk as long as I want to. But also that at my thesis defense I could sort of assume that almost everyone there listening had some physical background knowledge that meant I didn't have to go so much into the details of the physics of gravitational lensing. But here, since this is a video going out on YouTube where a lot of people with a lot of different backgrounds are watching and listening, I cannot assume that any of you are either educated in physics at all or has any background knowledge from strong lensing, astronomy, or cosmology at all. So I'm going to spend a little more time on the physics in this presentation, and a little less time on the results, but I'm going to introduce enough results to give you the general picture, the essential results, in order to understand what we can do with strong lensing, and more importantly perhaps what we cannot do. I'm also going to try to introduce some, since this is a video sort of in the spirit of what I have done previously on my YouTube channel, and trying to sort of get introduced also some general scientific concepts that we have here in science and physics in general. So yeah, let's get started. So this presentation, I'm going to sort of introduce to you first the theory of strong lensing. Then I'd like to talk a little bit about clusters of galaxies, which my thesis has been about, actually the mass of clusters of galaxies, in particularly the cluster I have been analyzing in my master thesis. Then I'll explain to you how in general we can model such gravitational lens systems, configurations, but also what I have particularly done. And finally, what it's all about, the results and what they mean. Alright? So first, strong lensing. Now, the first thing I would like to show you is sort of an appetizer, you could call it. An animation of what gravitational lensing actually is. You can see it here. So before I start the video, I'm going to tell you what we have. We have us out here, we the observers. Then we have what in this video is called the foreground galaxy. I will call it the lens. And here they call it the background galaxy. I will call it the source. And here is what we actually see. So let's start it. So what happens is that the light from the source gets bent around the lens, and then we will see it differently. As you can see here, it gets bent, and then this is what we see. The reason these, instead of having just a circular source, as you can see, which is what we actually see, instead we get these arcs, highly elliptical and highly magnified arcs. I will shortly explain that, but otherwise you can look it in my other videos about gravitational lensing, so I'm not going to spend so much time on it. You can check out particularly convergence and shear whereas convergence enlarges the images and shear sort of distorts it into these special shapes. Let's continue. So, even though you probably all know this formula here, especially the ones that believes that the Earth is flat, so we want to sort of refute this expression here. It's from Newton. He invented it, and what it generally says is that the gravitational force on between two objects is equal to the gravitational constant g times the mass of one object times the mass of the other object divided by the distance between them squared. So as you can see here, the Newtonian gravity doesn't really leave us much room to deal with objects that haven't got any mass, like photons, for example, the carriers of electromagnetic radiation, or light, as we call it in general. But Newton actually speculated that even though this equation here didn't leave room to for photons to be influenced by a massive object, he speculated that it could actually happen. So what we can also do is take this relation here between the force and the acceleration of an object, and then we can equate them to each other. So we get that m times a is equal to gmm over r squared. Now, as you can see, since we have little m on both places of both sides of the equality sign or the equal sign, we can remove them. So we get that the acceleration of some object with or without any mass is equal to g times the mass of the object doing the deflection divided by r squared, the distance between them. Now, as you can see here, I tried to take a picture of a drawing to show you what happens. So down here we have the object with the mass big M. R is the distance from M to the impact site, or the place where the photon here gets deflected. C is along the motion of the photon, so it's this way here. And these two parts here represent the force experienced by the photon from the mass here. Now, as you can see, as the photon moves towards this point here, the impact point here, that we have a general attraction towards M along this vector here. Now we can decompose this vector here into its constituents, so we have a force along the direction of motion, and then we have a force perpendicular to that towards M, or towards the mass M. Now, since after we have passed this deflection point here, we can also decompose this force vector here towards M into the vector along the motion, direction of motion, and a vector towards M again. Now, as you can see in this, I could have drawn a lot more force diagrams in here, but it wouldn't make any difference. It would show the same picture. So as you can see, towards M, along this direction here, along this direction here, yeah, you can see that the force is positive because we have this way here to be the direction of motion. But as we have passed the impact point, so this is not an impact. The impact point doesn't mean that the photon hits anything. It is where the deflection takes place, if you will. But in actual, the deflections takes place along another a longer place. You can see it's an arc here. But anyway, after we have passed this point here, we can see that now the force along the direction of motion is in the opposite direction. So from that we can say that since we have positive force here and negative force here, and that they are equal to each other at the same distance from this point here, they cancel out. So the only true force the photon experiences will be towards m, and that is the deflection. So you can say that towards m the photon will be accelerated in the positive along the motion of direction of motion, but after it has passed m here, down here actually, it will be accelerated in the opposite direction and in equal amounts. So the velocity that the photon had before it was deflected is the exact velocity the photon has after it has been deflected. Remember that at this point we are using Newtonian gravity and Newtonian theory of gravity. So we don't actually involve a finite velocity of a photon. Of course, a photon cannot travel more than the speed of light, but at this point we don't actually introduce this yet. So we can say that the acceleration the photon will experience is equal to, I will also written it down here, gm over r squared plus c squared, where c is along the direction of motion. But since there's only a perpendicular, again compared to the direction of motion, a perpendicular force experienced by the photon, we can rewrite it so we get that the perpendicular acceleration is equal to gmr divided by r squared plus c squared to the 3/3. So this is sort of a cubic root, I think it's called. No, it's a 3/3 cube. Yeah, root. Yeah. Let's continue. So in order to find the deflection angle, we can say, well, we can also find the perpendicular velocity to be equal to the integral of gmr over r squared plus c squared to the 3/3 dt, where we can say that dt is equal to dz over c. So we actually get this integral down here, and when we solve it, we get that the perpendicular velocity is equal to 2gm over c times r. So we have no r squared longer. Then we can say that the deflection angle we have is equal to the perpendicular velocity divided by c, and that gets us the velocity, or the deflection angle in Newtonian gravity, or Newtonian relativity if you will, is equal to 2gm over c squared r. Now this r here is the distance to the impact parameter point, so it can be something else, but here we call it r. In the Einsteinian gravity or general relativity we call it something else, but they are essentially the same values. So as we know now, gravity is actually not so much a force between two objects influencing each other, but it's a combination of objects with mass influencing space-time, and space-time's the shape of space-time influencing how objects behave. This is explained, if you will, in the Einstein field equations, as you see here. Now I call them equations because although you see one equation here, there are actually 10 different coupled equations, nonlinear coupled equations here. And this is expressed by the tensor part you see here, mu nu, which shows that this is a tensor. So what do we have? Well, we have here the Ricci curvature tensor. Here we have the Ricci, or the curvature scalar, Ricci curvature scalar, and then we have the metric here, g mu nu. The metric, if you can say, is sort of the ruler in space-time. Like when you take a ruler to to measure a distance, it's the same expression here. It tells us it's sort of a yardstick in space, if you will. So, and this part here with the curvature scalar, the curvature tensor, and the metric defines the curvature of space-time. Over here we have the energy momentum part. We have 8 pi g over c to the 4th times t mu nu, where t is the energy momentum tensor. In here somewhere is the mass buried, so we could also call this mass, but it wouldn't be explicitly correct. So I've called it energy momentum instead. So this part here defines the curvature of space-time, this part here defines the energy momentum in space of objects as well. So what you can say is, as you see here, if we put something massive in here, we get some curvature over here. This is expressed like this. You can see Earth, curved space-time. Now this is not a true representation, it's an artist impression. But as we have some curvature here, we can put in a satellite, and the curvature of space defines the energy momentum of that satellite, which essentially makes it want to take the shortest route around Earth, which is no longer a straight line, it's a curve. And that is usually one explanation why things tend to go around objects with mass in circles or ellipses, is because of this energy momentum relation between curvature of space-time and the mass of the object. So let's continue. So one idea could be that we would actually have to apply the full solutions of the Einstein field equations in order to work with gravitational lensing, but fortunately we can take a shorter route. So the first thing we need to do is to divide sort of the gravitational potential or the gravity into sort of a strong and weak regime. Now we define the weak regime as the gravitational potential divided by c squared. If this relation here is much less than 1, we are in the weak regime, whereas if this relation here is a little less than 1 or almost equal to 1, we are in the strong regime. If we are here in the weak regime, we are dealing with small deflection angles. If we are in the strong regime, we are dealing with large deflection angles. We see this here around black holes and neutron stars. So in the weak regime, we can linearize the field equations, which essentially means that we can treat gravitational lensing as a geometrical problem with a geometrical solution. If we're in the strong regime, we cannot linearize the field equations, and we instead need full solutions to the field equations. Now, when dealing with clusters of galaxies or galaxies themselves, we can say that the gravitational potential is sort of equal to the velocity dispersion squared. Now, for a typical cluster, the velocity dispersion is roughly 1500 kilometers per second. So I hope you all can agree with me on that if we take 1500 kilometers per second squared divided by 300,000 kilometers per second squared, this is indeed much less than 1, and we are in the weak regime. This means two things. Since we are dealing with small deflection angles, we can apply the small angle approximation. That means that instead of having to take the sine to the angle alpha, we can just take the alpha, the angle alpha itself. So from general relativity, what we really need is the corrected deflection angle alpha, gr, alpha hat, gr, is equal to not 2, but 4 gm of the mass enclosed within psi divided by c squared times psi. Again, psi here is the distance, a vectorial distance this time, nevertheless, between the mass m and the impact parameter of a photon. Alright? So I want to show you now, this is entirely not a part of my thesis, but I want to show you again to sort of give a general idea of how science might work. This is a very basic, very simplified example, but nevertheless it can show you an idea of how science might work. Now, as you know, these deflection angles comes from two different theories. One is from the Newtonian gravity, and the other is from general relativity, or Newtonian relativity, if you will. They can both be used to try to predict how, in this particular example, how a star will behave, or rather the light from a distant star will behave, because of course the sun is also a star, how the light from a distant star will behave if it travels very near to our own star, the sun. Now this has been done both using Newtonian relativity and general relativity, and gave two different results that could then be tested. So as you can see here, we use the values for the sun. We have our sun is equal to almost 7 times 10 to the 8 meter. We have the mass of the sun, almost 2 times 10 to the 30 kilogram. We have the velocity of light, the speed of light in meters per second. And then we have the Newtonian, the gravitational constant, 6.67 times 10 to the minus 11 meters cubed per kilograms per second squared. Yeah, just to be exact. Using these values, we can calculate the deflection angle using Newtonian gravity for the sun. That is the deflection of something, a photon, let's say that, at the limb of the sun, because I used the radius of the sun. And if we calculate that using Newton, we get 0.87 arcseconds. Doing the exact same thing using general relativity, again at the limb of the sun, we get 1.75 arcseconds. Now, this was tested experimentally, or actually using observations by Dyson and others in 1920. Actually, it was 1919, but the article was published in 1920. What they did was, at first they took images at a particular point on the sky of stars, where they knew in advance that there would be a full eclipse of the sun. And then up to the point where this eclipse would occur, they traveled to two different locations on Earth, one at the coast of Brazil, of South America, and one in Africa, at an island near the coast of Africa, as I remember it. So what they did was that they observed, took images of these stars during this full eclipse, and then they measured the deflection of all the stars they could see around the limb of the sun. And they found a value, as you can see here, a deflection angle at the limb of the sun of 1.61 arcseconds plus minus 0.30 arcseconds. So even if you account for this difference here, the discrepancy, it shows that the theory that best describes the deflection around the limb of the sun is general relativity. Now there are other examples that also is better explained by general relativity. If we look at the gravitational redshift of a spectra from the sun, you can measure that. This cannot be explained by Newtonian gravity. Also, even if you use the elliptical orbits of the planet Mercury, using Newtonian gravity and Keplerian orbits and so on, using elliptical orbits, you cannot explain why Mercury precedes. So that means that the orbit is not fixed, but sort of shifts a little bit around the Sun. And this is actually present for most of the planets, but it is particularly observable with Mercury since it's so close to the Sun. This cannot also not be explained by Newtonian gravity. So you can see a way to define the success of a theory is both its ability to explain something that haven't previously been explained, but also its ability to predict new observations that then can be tested later on. All of these things has been the case with general relativity. So, as far as now, it is the best explanation we have for gravity. Now you can also derive, gravitational lensing from general relativity, but it's just much easier not having to solve these 10 equations when wanting to model gravitational lens systems. Alright? So, let's continue on the theory of gravitational lensing. Now, as I said before, when we have a deflection from a lens, we actually have an arc. And that would usually mean that instead of calculating this as an angle, we would have to integrate over the deflection. But we can apply what is called the thin lens approximation, which simply means that if we look at the distances we usually have, we have an observer, we have a lens, and we have a source. So in this example here, we apply 3 distances, if you will. We have the distance from the observer to the lens, d capital L. We have the distance from this lens to the source, d capital Ls. And then we have sort of the physical extent, the size of the lens along the line of sight, dl. Now these distances here, d capital L and d capital Ls, is usually in gigaparsecs, whereas the physical size of a lens for a galaxy, it is typically in the kiloparsec regime, and for clusters of galaxies, it's typically in the megaparsec regime. So since, as you can see here, d capital Ls is much larger than dl, and again, d capital L is much larger than dl, we can simply squish the lens into a single plane, a 2-dimensional plane, which also means that we, instead of dealing with the deflection as an arc, we deal with it as an angle. This simplifies our procedure and makes the following possible. This is what it's all about. This is the core of the theory of gravitational lensing. I think I've introduced it in another video, but I will shortly go over it again. Now, we have some units I would like to introduce. We have the deflection of the image from the line of sight, theta, this angle here. Then we have the position, the true position of the source, defined by beta, which is this angle here. And then we have the scale deflection angle alpha, which is this angle here. And then we have the deflection angle alpha hat, which is this angle here. We also have the angular distance, if you will, from the line of sight to where we see the images in the image plane, E psi here. And then we have the distance, the angular distance from the line of sight to the position of the source in the source plane, which is called eta, which you see here. Again, we have the distances, the distance from the observer to the lens, dl. We have the distance from the lens to the source, dls. And we also have the distance from the observer to the source, ds. dl and ds can be found by finding the redshift of the source. We can do spectroscopy or photometry of both the lens and the images that we see, and then we can find these two distances here, and from these two redshifts here we can also find the distance from the lens to the source. Now these do not add linearly, so that means that you cannot just take dl plus dls and then get ds. This is because this is in what we call angular diameter distances. If we used another type of distance parameter or distance method, we could add them together just as easily. But in most modeling systems or most modeling methods, we use angular diameter distances. Alright, so these angles here are also called angular distances. So as you can see very easily actually, if we take theta, this distance here, and subtract the scale deflection angle alpha, this distance here, we get beta, which is this distance here, which is what is written here. This is the lensing equation or the ray tracing equation, and it is the most fundamental equation in gravitational lensing. Now, since this is a two-dimensional representation, but all of these distances here, psi, alpha, theta, beta, eta, and so on, alpha hat, are two-dimensional distances. So that is why they are all vectorial. We can also see that if we look at the deflection angle, scale deflection angle, and the deflection angle, we can find that this distance here is equal to the scale deflection angle times ds, but also that the same distance is equal to the deflection angle times dls, as I've written here. And finally we can see that psi here can be defined as theta, this deflection angle here, times dl, this distance here. So this is just simple geometrical solutions. Now by shuffling these two equations up here a bit around, we can get to a new representation of the lensing equation, where we have the lensing equation, the deflection angle here, not the scale deflection angle, but the deflection angle, and some distance ratio here, dls over ds. Now at this point it might be tempting to also add the deflection angle from general relativity, but since we are introducing a mass part by doing that, we also need to make some kind of assumption about what kind of mass we are actually dealing with. Is it spherical, elliptical, what shape does it have, and what is the density and distribution of mass within it. So that we will do in the next part here. For example, we can assume a spherical mass assumption. So even though this is not truly a model, by assuming a spherical mass distribution and also setting the lensing equation in one dimension, we can find this value here, theta e, the Einstein equation, as the square root of 4gm of the mass, spherical mass enclosed within theta, divided by c squared, and then this distance ratio here, dls over ds times dl. Another true mass model that we can use that also assume a spherical mass distribution is the point mass lens, where the lensing equation becomes beta is equal to theta minus the Einstein radius squared times 1 over theta. And this is also in one dimension. Now, this point mass lens equation here has two different solutions. This is illustrated on these two plots down here. Now, for the point mass lens, you can see that these two curves here, gray curves, solid curves, represent the possible image positions. The dashed lines here represent the position and size of the source. And these two vertical solid lines here represent the magnification and position of the two images. As you can see, we have image 2 out here, relatively close to the center of the lens. It is demagnified, actually highly demagnified. We also have an image 1 out here, somewhat more distant from the center of the lens, but magnified. Another way to represent this is to plot the position of the source with respect to the position of the images. The black dots here represent the different position of source, and the blue and red curves here represent the different position of images. So as you can see, if we have a source position at the outskirts of this plot, -2 point -2, we have one image very close to the source, which is almost maybe a little magnified, but neither highly magnified or highly demagnified. And then we have another image very close to the center of the lens, highly demagnified. And as the source moves closer and closer to the center of the lens, you can see that this image here will not only become more magnified, it will move away from the center of the lens and then finally move towards the source. Whereas this image down here, which started close to the source, will move further and further away towards the center of the lens and become more and more demagnified. Now, at the exact center of the lens, we have two images equidistant from the source, which actually defines or represents an Einstein ring. This can also be defined by this equation up here, which shows that for spherical mass, when the source is at the position, is at the exact center of the lens, along the line of sight, of course, we'll get an Einstein ring, which is plotted or positioned where the image is positioned exactly along the Einstein radius. So this is just a simple model. The model that I've used to represent a cluster is of course much more complicated, but nevertheless the principal ideas that you have seen here still holds. So let's continue. This is an image of how it could look. This is what we call galaxy lensing. We have a galaxy here, large, massive galaxy, and then we see these images around here. As you can see, this is almost an Einstein ring. So the source would probably positioned very close to the center of the lens, along the line of sight, of course, again. But we should also notice that there are other galaxies around this galaxy here. So we would also have to assume that these galaxies here, as you can see them, might influence the position, not the amount of images, but the position. They will perturb the images. And as you can see, this is not an entirely circular image position. This may be partly due to that this mass in here might be elliptical, which it probably is, but also the perturbing, what we call external shear, the perturbations conducted by galaxies around this lensing galaxy here. What I have dealt with in my thesis is not galaxy lensing, but it's lensing around clusters of galaxies. This gives many more multiple images. We have different sources and so on and so on. So let's introduce clusters of galaxies, and in particular the cluster I have modeled or analyzed, MAX J0416.1/2403, or as I will call it henceforth, just MAX. Here you see two typical examples of clusters of galaxies. Over here we have Abell 1703, and over here we have Abell 2218. Now, as you can first and foremost see, we have these giant arcs, and you might also be able to see that there are many multiple images around this cluster, indicating that this is a very massive object in space. You can also see a very strange configuration here. We have 4 circular position images around these 2 galaxies here, and then we have a 5th image somewhere around here. The general idea is that this is a relaxed unimodal cluster. Now, in order to see this particularly, you would have to look at also the X-ray emission from the cluster. But in general, you can say that all of the mass in the cluster seems to be somewhat evenly distributed around this bright cluster galaxy here. You can also see that the images, the arcs, seems to be defined so that they are, or be positioned so that they are bent around this mass center here. If we look at Abell 2218 instead, you can see we have a massive galaxy here, a bright cluster galaxy here, but we also have something here that seems to be massive. You can see that some of the cluster members seems to be concentrated around this galaxy here, but there are also cluster members concentrated about these galaxies or around these galaxies here. You can also see it on the multiple images. You can see arcs here, but we can also see arcs highly distorted around this part here. This initially suggests that this is a bimodal, non-relaxed cluster, possibly either undergoing a pre-merging phase, which means that we are seeing these 2 parts, this part here and this part here, merging for the first time. It could also be a post-merging scenario where the galaxies have merged one time, the clusters, these 2 cluster parts here have merged one time, but are then moving towards each other again for a second merger. These are generally described as either pre-merging or post-merging scenarios. Again, it is evident when you look at the X-ray emission from such a cluster here, a non-relaxed bimodal cluster, that you have 2 not equally intensive but 2 separate emission centers, and that is also evident in MAX, as I will show in a couple of slides from now. So what we know about MAX already, as I said, is that it is a non-relaxed and bimodal, possibly trimodal structure. A recent study by Kamina and others from 2016 suggests that this is actually a trimodal structure, which means that there are 3 mass centers in this cluster. It has been shown to have a flat inner core. We usually divide, I will explain in more details when we come to the results, how you can see that it has a flat inner core. We usually divide this cluster into a northeastern and southwestern cluster halos, 2 parts. From the VMOS VLT study, the Very Large Telescope, we have found over 800 confirmed cluster members, whereas 144 are in the core. Now this is 144 found by spectroscopy, also using the new MUSE instrument, also on the VLT telescopes. The cluster is found to have a redshift between 0.394 and 0.4. And this is not due to the two separate cluster parts, the northeastern and southwestern, but simply because the cluster, as I said, have a physical extent along the line of sight. So here you see the hot gas or X-ray emission from MAX. As I said before, you can clearly see that we have two emission peaks, one here and one here. This is also indicated both by using the, I should say this is an image from the Chandra Space Telescope. This is highly evident when you look at the centers found by the Chandra reduction software package, defined as red crosses here, one center here, one center here. But also if we use the IREF reduction package or IREF analysis package, which is defined by the black crosses here, and the black circles here, the black dashed circles represent the full width half maximum of the IREF centers. The white dashed line, the white dashed circle out here represents the limit of our mass analysis. It defines a 400 kiloparsec radius from the barycenter around here. Alright. You can also see from this the X-ray emission that MAX has a highly elliptical, highly elongated shape. If we look at data, X-ray emission from relaxed cluster, it would be more circular in shape, suggesting that the mass would be equally distributed around this mass center, which is often, if not always, the bright cluster galaxy, BCG. Alright, let's continue to the method, the modeling method. So first of all, I have used Lens Tool. The article I have based my analysis on by Grillo et al. From 2015 used a program called GLEE. In basics, they do the same thing. You can use different priors, different parameter values, but it is a parameterized modeling of a gravitational lensing configuration. Now, Lens Tool is publicly available. It is also publicly available source code, which means that anyone with knowledge about gravitational lensing modeling and C code can edit and contribute to the code. It was created by, now I hope I pronounce his name correctly, Jean-Paul Knight, in around 1990s. I think the official date is 1994, but as I understand it, he also used Lens Tool, or sort of created the basic part of Lens Tool in his PhD thesis, which was around 1990. Lens Tool uses both chi-square reduction or chi-square optimization, but also a Bayesian optimization method. Now, the advantage is that the chi-square gives you the best fit, but the disadvantage is that the way we explore the parameter space, that is, shift the parameter values around to find the best fit, you can actually end up in what is called a local minimum of the chi-square, instead where the best solution would be the global minimum. And that is because when you shift a parameter value, when you explore the parameter values, if the chi-square is reduced, then you sort of define or limit the parameter value exploration of that particular parameter value at that location. But you might as well have moved it 2 steps to the other side and found an even lower chi-square, but you'll never know that. And that's not only for lensing, but in general, the disadvantage of using chi-square reduction as a way to find the best model. So that is why another guy called Eric Jullo included Bayesian optimization, where instead of just finding the best chi-square, you explore the entire parameter space to find sort of the optimal parameter position and then you take these parameter values to sample different parameter values for all the models, possible parameter values, and each sampling define a particular model with particular parameter value sets. Now, in LensTool you can do two things. You can set two things. Initially, you can set what is called the burn-in parameter value. It is a value that defines how well you explore this sort of large parameter space that you have. The lower the value, the more you will shift the parameter values around a little bit, but it will also take longer time. The other thing is that you can say how many samplings you want. Now, of course, the more samplings you include, the better you will explore your parameter space to find the best model. But when you want to do analysis of the errors in your model, you will also have more parameter values, more different models to work with. I will show you how that looks later on when we look at the results. Now, LensTool takes at least two files to run. First, you have sort of the general parameter value parameters file, where you introduce your parameter values that you want to optimize. You want to set the sort of general behavior of LensTool and all sorts of things. But you also need a list of the multiple images that you want to use for constraints, because if you don't have any constraints, you just have a lot of free parameters, and that won't do anything useful. So, and a general rule of thumb is that the number of free parameters that you have in your model must never exceed the number of constraints that you have. So, for example, if you have 100 constraints, you can maximally introduce 100 free parameters into your model. Now, as you can see here, we get sort of an evidence, the most likely model. Now, another good thing about the Bayesian optimization is that it has been introduced or implemented in such a way that it will always favor the most simple model, because you can always get a better fit by adding more free parameters. The more free parameters you have to shift around, the better fit you can get. That is sort of a fundamental behavior of chi-square reduction. But if the more parameter values you introduce into your model, if LensTool finds that you might have an equally good fit with less parameter values, it will penalize you for adding more parameter values into your model. So LensTool will sort of generally favor not only the most likely model, but it will also favor the most simple model. You can call it LensTool's version of Occam's razor. And finally, what I want to say is that LensTool uses OpenMP for multi-core or multi-processing optimization. This means that if you have a computer with, let's say, 16 cores, then you can utilize all 16 cores for optimizing your code, your system. But it does not introduce the MPI architecture, which means that if you have, let's say, 4 computers with 4 cores each, that is 16 cores all in all, you can only utilize one computer with the 4 cores to optimization, because it does not have the MPI architecture. All right. So my modeling method for analyzing max is what has been done by Grillo et al. 2015 again. I use 1 or 2 cluster halos, either using a dpi, piamp, or GNFW, a generalized NFW profile, where in order actually to use the dpi profile, but in order to sort of emulate a piamp profile for a cluster, I set the scale radius to approximating infinity. That is a very large number indeed. So 1,000, 10,000 kiloparsecs, something like that. Also, I include 175 cluster members, again from the paper, Bailey et al. We use dpi profiles where a dpi profile where you set the core radius to approximately or approximating 0, going towards 0, best describes has been found to best describe galaxies. Cluster members are galaxies. So in actual numbers, we set it again to a very low number, for example 0.15 or 0.05 kiloparsec, something like that. Also, again from Bailey et al., we get 30 multiple images distributed in 10 different systems. And what has been shown previously in a number of studies, all the way back to Johnson and others from 2013, I think it is, we have to include a foreground galaxy at redshift 0.114. Now, since we are not dealing with, as you saw before in the theory, we have only one lensing plane. This is also the case in our modeling codes. So we are dealing with a single lensing plane modeling code. But since the foreground galaxy, as you can see, is at a different redshift than the cluster we set to redshift 0.396. In order to include this foreground galaxy in a truly physical, meaningful way, we would have to apply two lensing planes. One lensing plane for the cluster itself and one lensing plane from the foreground galaxy. Now, the reason we have to include the foreground galaxy is that we can see that there are multiple images not created by the foreground galaxy, but around the foreground galaxy. So we can definitely not assume that this galaxy does not influence the position or distribution of these multiple images. Now, the way we include the foreground galaxy is sort of a hack method, where we set the redshift of the foreground galaxy as the same redshift of the cluster, which is definitely wrong, but then exclude the foreground galaxy from the mass analysis. Now, we can do that because we only want to find out, we only want to shift the mass of the cluster that we have and the cluster members by the amount that this foreground galaxy might influence the position of the multiple images. Now, if the foreground galaxy does not have any influence, then it won't matter, because then we just have included a set of parameters that are useless, and then we would see it in our evidence and we can exclude it, but it has been shown to matter, so that's why we included it. Also, all of these things I have mentioned up until now has been conducted previously, so what have I done? Well, one of the things that I noticed that haven't been done previously on this cluster is to use elliptical cluster member profiles. Now, the name elliptical cluster member profiles is not truly correct, but it's just to be in opposition to use strictly circular cluster member profiles. Circular cluster member profiles, where you define all the mass distribution of all the cluster members as being circular, is what has been done previously. But what I have done is to say, well, the usual approach actually is to say that the mass of a given cluster member traces the emission of the light. That is why we call it elliptical cluster member profiles, because an ellipse can also be reduced to a circle, but a circle can never be an ellipse. So yeah, I'll show an example in another slide. I also used optimized scaling relation slopes instead of fixed scaling relation slopes. Again, I will explain what these scaling relations actually are and how we use them in another slide. And finally, the redshift of the cluster, as I said before, has been fixed or set to 0.396. Alright, so here you see an example of circular cluster member profiles here, actually this is an exempt of the mass estimate from the final lensing code or lensing analysis, as opposed to where you set the mass of the cluster members to trace the emission of light. As you can see, some of the cluster members are highly elliptical, some are almost circular in shape. So this is the only difference that these two makes, but this has been the standard for MACs up until now. And also the cluster member scaling relations, they are defined as such. If we have the scale radius and the velocity dispersion of a given cluster member, we can find that by using these scaling relations here. We use a reference scale radius and a reference velocity dispersion. This means that this is the velocity dispersion and scale radius of a reference galaxy. These two values are optimized in Lens Tool. Then we take and multiply that with the ratio between the luminosity of that galaxy, that cluster member, divided by the luminosity of the reference galaxy, to some exponent which is defined as these scaling relation slopes. As you can see it both here and here. As I said before, these two values here are optimized in Lens Tool. These two are derived from the magnitude, which is what we get for the cluster members. And these two scaling relations here, this down here for the velocity dispersion and this up here for the scale radius, can either be fixed or optimized. Now, when we fix them, we can sort of use two basic numbers. We can set the scale radius slope to 4. That is the value for constant mass to light ratio. It gives a slope of 0.5, 1/2. We can also set the scale radius slope to 2.5. This is consistent with the fundamental plane and gives an actual slope of 0.8, almost 1. Or, as I said, the third option is that we can optimize these values. There's no in Lens Tool, there's no value consistent with these two fundamental plane or constant mass to light ratio, but the standard is to set this to 1/4 or 0.25. Alright. So here the list of the models. I will not explicitly explain all of them, but I will show you or sort of explain the basic idea behind them. So up here we have two models where we include only the cluster member cluster halo profiles. That is 2 pi-empt or 2 NFW profiles, nothing more. Then we have one model here where we include 1 pi-empt, that is 1 cluster halo profile. We include the 175 cluster members plus the foreground galaxy using d-pi profiles with circular mass distribution. The mass to light ratio here, defined as 0.2, indicates that we are using fixed scaling relation slopes. Now, if we look at this example here, this example down here, again, here we include 2 cluster halo profiles as opposed to 1. Again, we include the 175 cluster members, the foreground galaxy, but here we model them as elliptical d-pi profiles, or profiles where the mass is assumed to trace the light. And also over here we have the mass to light ratio set to V, which I define as variable, which means that we're using optimized scaling relation slopes. And then you can see we also include NFW profiles and so on and so on. Here you see the position of the multiple images that we have. The numbers indicate that they are from the same source, as do the colors, but you cannot trust the colors alone because 2-point models over images here are not from the same source as the 8-point models over here, sources, images over here. But in general, you can see that we have images sort of distributed in a elliptical shape around the cluster. Alright. Here you see the cluster members. Again, you can see that they are almost circular in shape, but along inside here, close to the core, they are more elliptically distributed. This is also consistent when we look at the results, which we will do now. So let's look at the results. First of all, I find that the best fitting model is a model using 2 pi profiles, the 175 cluster members plus the foreground galaxy, modeled by circular d pi profiles, and using optimized scaling relation slopes. Now, in true numbers, we actually find that the elliptical cluster member profiles, or the cluster members profiles where we assume that the total mass will trace the light, they give the best fit in numbers, in actual numbers, both with respect to the chi-square, but also the evidence. But since the difference between the circular best model and the elliptical best model, especially around the evidence, is so much small, it's not very big, and also given the fact that the elliptical models, the model using elliptical cluster member profiles, take a lot longer time to optimize, we surmise that the best model to use, it's actually the one using d pi, circular d pi profiles for the cluster members. But we get the absolute best fit using optimized slopes. So I would like to show you now a representation where we look at the luminous matter, that is light from the cluster. Then we overlay or superimpose the X-ray emission in red, the dark matter distribution, or actually the total matter distribution of the cluster halos, in blue. And then you can get sort of a nice visual representation of how it looks, how it's distributed. So let's start. First we overlay the X-ray emission in red. So you can see it here. Then we remove it and put in the dark matter distribution in blue. As you see it here, we actually have a center here, around here, and one here. And then we overlay them on top of each other. So first the X-ray emission, and then the dark matter distribution, as you can see here. Now, the center of the X-ray emission and the dark matter distribution, mass distribution of the cluster halos, is roughly here, but we also have a center roughly here. I will show that in more detail in another plot. I think it's the next slide, perhaps. Yes, so you can see here. First of all, you can see that the distribution of the cluster halo mass is highly elliptical, elongated, shifted a little bit towards the east, a little bit only, but still you can see it's evident. You can also see that there's a larger difference between the center found by the mass analysis, which is defined as a white star, as opposed to the centers found by X-ray, which is a red dot. The same down here, but there is the difference between the two much less. And again, just to be precise, the white contour lines define the distribution of mass from strong lensing analysis, and the red contour lines defines not the mass distribution, but the emissivity or the emission distribution from X-ray. And as you can see, the density of emission is much larger in here towards the centers than they are out here, and we see the same thing, that the mass distribution from strong lensing gives a lot higher density in here around the center of the two cluster members here than in the outskirts. So let's look at some of the physical explanations when we are talking about these statistical errors that we can get. I've selected two different ones to sort of show you how we can actually derive physical understanding from such a statistical error. Now, all of these dots, if you imagine that there were dots in here, represent a single model from a lens tool. All in all, we have 10,010 different models. We have actually 1,001 different models, but we have 10,010 different chains to work with. So all of these will define different parameter values of different models. Now, the contour lines in such a plot is that the inner contour line is 1 sigma, or 6 to 8% confidence interval. This basically means that we are certain that we are 68% certain that our best parameter value will be within this parameter space here. The next contour line represents 2 sigma, or 95% confidence interval. If you have read medical studies, you will probably know this 95% confidence interval or 5% error interval. This basically means the same, except that here we are 95% certain that the best parameter value will be within this space. And finally, the outer contour lines here represent 99.7% or 3 sigma, which again means the same thing, that we are 99.7% sure that the best parameter value will be within here. This is the same over here. On this plot, we have positioned the x and y center of halo 1. Over here, we have plotted the core radius compare with the velocity dispersion again of halo 1. So let's look at the position. As you can clearly see, the positions are anti-correlated. This means that if I decrease the position of x, I can also increase the position of y and still be within the best parameter value set. As you can see here, I can actually go all the way out here up to all the way up here and still be 99.7% confident that I am still having the best parameter value set. Now, the red dot here with error bars indicate the best parameter values from our model. I will explain in the next slide a little bit about what this actually means physically. So let's go over to the other, over here. As I said before, we have the core radius and the velocity dispersion of halo 1, that is the cluster halo. Now, as you can also see here, these values are correlated, which means that if I increase the velocity dispersion, I can also increase the core radius and still be within the best parameter value set. I can still be 99.7% confident that I'm having a good model. Now, what does this mean? Well, it means that these parameter values here are degenerate. They depend on each other. So, in physical, what this means physically is that the total mass of the cluster is defined by the position of the multiple images. So, in a sense, you can say that the total mass of the cluster is fixed. Now, this is also evident when we look at different mass analysis of max. They don't deviate much from each other. They are in the same ballpark, if you will. But the parameter values might deviate from each other depending on how many parameters has been included, how they are included, what you're optimizing for, and so on and so on, what your constraints are on the priors, how much parameter space you have allowed yourself to have. But the general idea is that if I increase the velocity dispersion of a cluster halo, this here, I will increase the mass of the cluster halo. If I increase the core radius of a cluster halo, I will decrease the mass. So as you can see here, I can increase the velocity dispersion and then equivalently increase the core radius, as you can see, and still have the same mass of that cluster halo. Now, of course, there is values that gives the best model that is also defined by the red dot with the error bars, but it's just to show you how you can statistically show and derive physical understanding from these models. Also, another thing is that, of course, I have selected two examples here where we have respectively anti-correlation and correlation. You also have parameter values that are in no way degenerate, that don't depend on each other. Then you will have a nice non-symmetrical distribution around it here. Alright, so this is just to show you that we can actually derive physical understanding from these models. Let's continue. So here you can see how the parameter values are degenerate. That is, let's look at the position of cluster halo 1. We have that up here. First of all, we have BCG1. This is the bright cluster galaxy here for halo 1, if you will. And then we have BCG2 down here, the bright cluster galaxy for halo 2 down here. Then we have the foreground galaxy G3 down here. Alright, let's look at halo 1. As you can see here, this dotted or dashed ellipse here represents the core radius from the model. As you can see here, if I look at the center of halo 1, this is the best model center of halo 1, I can shift the best position along this direction here without changing the mass distribution that much, right? But if I move it along this direction here, I cannot move it very much without changing the mass distribution. If I move it out here, I will change the mass distribution significantly. If I move it over here, I will not change it that much significantly. Of course, this is the best position found by lens tool. And the same goes on down here. I can move it in this direction here, the center of halo 2, along this direction here, without changing things that much. But I cannot move it along this direction here without changing things that much. This is what you see here. I can move it along this direction here, but I cannot move it along this direction here. Then I can move it all the way up here and still be 68% confident that I am within that I'm having the best fit. But I can only move it a little bit. I can even this much here, which is not that much, until I go out beyond. If I go out here, then I am no longer 99.7% confident that I'm having the best model. Alright, so this is what you can derive by this Bayesian method. If you only used chi-square method, then you couldn't get something like this. Alright, let's continue. So another thing is that we can also have systematic errors in our modeling. Now, there's no measure in lens tool that can show you whether you have systematic errors. What you can do in order to see if you have systematic errors in your best model is to try to do some analysis of all the models you have. So that is what I have done here. Here you can see the surface mass density estimate from lens tool, I suppose, compared with the radius out to 400 kiloparsecs, as I said before. All the little lines here represent the position of multiple images, and you can see here why we have cut at 400 kiloparsecs. We have the final multiple image out here. Now, as you can see here, when we look at the surface mass density of all these different models, both using 2-piant and NFW profiles is that they don't deviate that much, particularly when you look at the total mass, total surface mass density, or the surface mass density of the cluster halos. They are almost on top of each other. So there's evidently no systematic errors here. And even when you look at this difference here in the cluster members, where there are much more difference, they deviate more from each other. They follow the same trend, which also suggests that that there are no systematic errors. Now, the reason why these surface mass estimates here deviate more for the cluster members compared with the cluster halos is that in order to define the mass around a given object, that be it a cluster or a galaxy, we need to have multiple images. Now, for clusters of galaxies, we usually don't have multiple images around the galaxies themselves, the cluster members themselves. There might be multiple images generated by the bright clustered galaxies, but in general, it is the cluster itself that generates the multiple images and the cluster members that perturb the position a little bit. So in order to constrain the mass around the cluster members, we would need to have multiple images around all of them. But since we don't have that, we cannot constrain the mass, or in this case the surface mass density, that well. But as I said before, we can see that even for the cluster members, they follow the same trend all the way out from 10 kiloparsecs to 400 kiloparsecs. This all in all suggests that we also have no systematic errors in our modeling, in our analysis. Alright. So, as I said before, we know from previous studies that MACS has a flat inner core. And you can see what that means here. If we look at this is the surface mass density. If we look at the cluster halos here, or even the total mass up here, we can see that all the way up to roughly 100 kiloparsecs, the surface mass density is almost constant. It is flat. So that says two things. First of all, we can indicate, this indicates that MACS has a flat inner core. This means that the surface mass density is, quote, flat. It's not flat in that sense, but it is constant all the way out to 100 kiloparsecs, roughly. This also means that the core radius of the cluster itself is also roughly around 100 kiloparsecs. If we look at the total mass, the cumulative mass for the cluster, we can see the same thing. The mass, remember this is a log-log plot, both of them. So we can see that the mass rises almost linearly in a log-log plot. It rises almost the same all the way out to 100 kiloparsecs and then deviates a little bit downwards. Furthermore, this is a comparison between our best model, and the one resembling the model from Grillo et al. From 2015, which we call GRHA, Grillo, Hansen, to call it something. As you can see, they are almost the same. One thing is that you can see that the best model seems to put a little bit more mass into the cluster members, particularly in around the center where we have the most massive cluster members, but a little bit more in the outskirts where we have the least massive cluster members. We can also see that the total mass, both the mass of the cluster halo, but also the total mass, seems to deviate a little bit for the best model, suggesting that the best model puts a little less total mass into the cluster than our GRHA model. Other than that, they trace each other pretty well. You can also see clearly that what we would expect, that the cluster halo, the halos of the clusters themselves define almost the total mass of the cluster. The cluster halos define something, but not nearly as much. All right. So let's take a little more detailed peek at the scaling relations. Now here you have the numbers from our best model, the model where we scaled the scaling relation slopes. You can see we find a scaling scale radius of 105.3 kiloparsecs. As you can see here, it is very, very badly constrained. You can see that by the error bars here, that one of the error bars is much larger than the other. As opposed to the velocity dispersion, it seems to be relatively good constrained. And also you can see here that the scale relation slopes, the errors, also indicate that this is relatively good constrained. This is more badly, but in general they are okay. As you can see here, when we compare this number here, 0.39, this is the fixed number, 0.5, and here we get 0.59, and the fixed number is 0.35. Now, this doesn't really say much. You can look at the numbers and say, okay. But in order to represent it a little better, I've plotted it. So let's look at it. So the two vertical dashed lines here represent the dimmest galaxy that we have in our cluster member catalog, and this dashed line up here represents the brightest galaxy that we have in our cluster member catalog, and this is in magnitude, AB magnitude, both of them. Here we have the scale radius, and here we have the velocity dispersion. So let's look at the scale radius first. As you can clearly see, when you look at the dimmest galaxy that we have, if we look at the fundamental plane, the scale radius would be below what we can see here. It would be below 1. So we might not want to consider a constant fundamental plane model. If we look at the constant mass to light ratio, which is also the equivalent of the fixed model over here for the velocity dispersion, we can see that for the dimmest galaxy, the scale radius is less than our best model, as you see here, suggesting from this alone that our constant mass to light ratio, the one with fixed scaling relation slopes, puts a little more mass into the dimmest galaxies. Whereas if you look at the brightest galaxy, it's almost the same. There's no real difference between neither the fundamental plane, constant mass to light ratio, or the best model. This is different when we look at the velocity dispersion. Again, if we look at the dimmest galaxy that we have, you can see that our best model gives a lot less velocity dispersion from the dimmest galaxy compared to our fixed model, or the best model, the fixed model, suggesting again, like I said, remember that the dimmest galaxy is probably in the outskirts of the cluster. Probably, not definitely. But again, you can see that the constant mass to light ratio model, or the fixed parameter, fixed slope model, will put more mass into the dimmest galaxies, but this changes when we go above roughly magnitude 18.5. Then suddenly our best model, if we take for the brightest cluster member, you can see that our best model gives a higher velocity dispersion than the fixed model, indicating that all the galaxies above magnitude 18.5 will give more mass in the best model compared with the fixed model, where all the cluster members roughly below magnitude 18.5 will give more mass in the fixed slope model. Now, here you see sort of a diagram showing how many galaxies we have in our catalog with respect to the magnitudes. And as you can see clearly, that for all the galaxies below magnitude 18.5, the majority of our galaxy cluster members are that. But since these galaxies here, the brightest ones, are also the biggest ones, they will have a significant portion of the total mass of the cluster members. So even though there are more dim galaxies in our catalog, which will favor the fixed model, the brightest cluster member galaxies will get the most mass in our best model, suggesting that our best model actually puts more mass into the cluster members, which is also the case when we look at the numbers. So let's look at the mass distribution of the entire cluster. Our best model finds that the total mass at 400 kiloparsecs is 3.82 times 10 to the 14 solar masses. So this is a roughly okay big cluster. You can also again see that the distribution is highly elongated, elliptical. So let's look at the mass distribution of the cluster halos. Again, you can see the ellipticity, the elongation, but you can also see the deviation towards this point here. This might suggest that we have something here, another cluster halo perhaps, and this is actually shown to be true by a recent study by Kamina et al. From 2016, where they included a third cluster halo here, giving a better fit. Our model gives a halo total mass at 400 kiloparsecs, or 3.15 times 10 to the 14. As you can clearly see, the majority of the mass is within the cluster halos themselves. What's interesting by looking at the mass distribution of the cluster member halos is that in the outskirts the distribution is almost circular. But as we go towards the center, or the core, the distribution gets more elliptical. This might suggest that we are dealing with a merging scenario, but we cannot conclude it from this data alone. Now, as you can see, the total mass of the cluster members at 400 kiloparsecs, the cumulative mass that is 6.7 times 10 to the 13 solar masses. So this is a significantly less mass in the cluster members than the cluster halos, which is also what we would expect. This also explains why the cluster members themselves usually don't generate multiple images. They simply don't have the mass compared with the cluster halos. They have a significant portion of the total mass. Alright, let's continue. So I've done a literature comparison between all the different works that have been done on max. As you can see here, that the Johnson et al. Paper was not from 2013 but 2014 instead, but nevertheless. As you can see here, the masses within some reasonable discrepancy agrees on the same cumulative mass at different radii. So at 200 kiloparsecs they all agree almost. They deviate a little bit more at 250, and our best model deviates, as you can see here, both here and here, both at 250 and 320 kiloparsecs. So this is the kiloparsecs I might should have told you is the difference, is the distance from the barycenter that we have calculated and then outwards in circles. So it's a circular distance, and this defines the total mass, the cumulative mass that we have found within such a radius. We also done another literature comparison. Here we have the gray area here is the 1 sigma confidence interval mass estimate from weak lensing. Then we have the total mass from the Grillo et al. 2015 paper in black, again 1 sigma error bars. As you can see, the error from weak lensing is much larger than the errors from strong lensing, suggesting that strong lensing can constrain the mass better, but weak lensing can go way further out than strong lensing. Simply because the multiple images, as you can see here, are only around the core of the cluster. In red we have the GRHA model, and in blue we have the best model. As you can see, the blue deviates a little bit less downwards. We might want to investigate whether this is also evident if we add more multiple images, as has been done in the Kamina et al. Paper from 2015. They found almost 100 multiple images, as I remember it. Alright? So one other thing is that we can look for new member candidates. Now, as you can see here, our best model actually predicts 2 new images around here. It is from the source 7.3, as you can see here. Now, if you have watched my other videos about gravitational lensing, you would know that these lines out here are the outer caustics, and these lines in here are the inner caustics. So if we have a source outside the outer caustic, we'll have 1 image. If we have a source inside the the outer caustics, we would have 3 images. And if we have a source inside the inner caustic, we would have 5 images. So we have already supplied 3 images from the 7-point system, and then our best model suggests 2 more images. Now, as you can see here from the Hubble data, we don't see any new images here. So what we can do is to look at the predicted magnification of this system. Now, the magnification for candidate 1 is it's highly demagnified. And also, if we look at the, sorry, not the magnification, the amplification, if we look at the amplification for candidate 2, it is almost the same as the source. If we compare that with the other images that we have supplied, we get amplifications of 3 to 5. So this might suggest that either these 2 images are due to a faulty prediction. You can see that 7.3 is almost at the outer edge of the inner caustic. So if we move the source a little bit around, remember this is not the true position of the source, this is the predicted position of the source from the multiple images. If we move it a little bit around, we don't get these predictions here. This is also evident from the other model that we have, the GRHA model. It doesn't predict 2 new images. But even if the images were to be correct, true, then the amplification suggests that we might not be able to observe them. Said in another way, they will simply drown in the light from this cluster member here. Alright. So, to summarize, we have found that MAX can best be modeled using 2 cluster member halos, which has also been shown previously. We have found an highly elongated elliptical shape, which is what we would expect from a merging cluster. It has a flat inner core, again suggesting that this is a merging scenario, either pre-merging or post-merging. It has a bimodal structure. This is what we find. As I said before, Kamina et al. Have found evidence for a trimodal structure. And again, to sort of further that, the northeastern halo seems to be highly offset, suggesting that we might have to put a 3rd cluster halo around that point. We surmise that it is still best to use circular cluster member profiles to model MAX, but not to use fixed scaling relation slopes, but to optimize the scaling relation slopes. So this is it. I hope that you have sort of gotten a better idea now what we can do with gravitational lensing. Now, this is of course not something that could cure any illnesses or give us a lot of money, start new firms to generate a lot of cash, but hopefully it can make us more clever, give us more knowledge about the universe that we live in. Sort of like the same thing when you read the Bible or the Quran or something like that. You try to gain more knowledge about our existence, our place in the universe. Now, where you can say that the religious text sort of uses a historical approach, or sort of an idealized approach, where you sort of think about it. You assume that there's a higher being of some sort that has created this wonderful universe that we live in. We try to sort of take an approach where we use the physical knowledge that we have to generate theories about how things might be, how the universe is, how it's distributed, how galaxies are created, how clusters are created, how the universe itself was created. And then we try to get some quantities, some quantified knowledge, some numbers in essence, that we can compare with observations. And again, like I've said many times before, what is the best explanation is in physics is not the truth, because the true explanation suggests that there is some explanation that is the correct one. And even though it seems reasonable to think like that, I think it seems reasonable. And in some sense, this is also what physicists do. We try to find the truth, right? But the way we work in science suggests or defines that we can never find this truth. We can only find the most probable explanation. And if you sort of think about it, the truth is absolute, right? You can read in the Bible and find that God exists. It's the truth. He exists. End of story. We cannot do that in science, because our truth in science is only as good as the evidence, the observations that we have. If we find new observations that is no longer consistent with our truth, then we have no truth. Then our truth is false. And it also goes back to what I've said many times in my previous videos. In science, we cannot prove anything. We can only refute something, an idea. And if you think about it, it makes perfect sense. Because, as I've asked so many times, how many experiments do you think you have to conduct before you have proven something to be true? Is it 1 experiment? 100? Is it 1,000? How many? And the problem is that you would need an infinite amount of evidence to prove something to be correct. But you ideally only need 1 piece of evidence to refute something, some idea. So this is the way we work in science. We try to compare our theories, our hypotheses, with evidence, with observations. And one clearly good example that I have shown you here today in this video is the difference between the Newtonian gravity and general relativity. Now, before Einstein, Newtonian gravity was the truth, right? It was the best explanation that we have. And at that time, the scientists also worked a little bit different, which is also why we usually define these equations as the laws, the Newton law of gravity, the Newtonian law of motion, and so on. But as we sort of advanced our observations, we got better to observe, we found that the Newtonian model of gravity could not explain what we actually saw. And as I said, sort of the epiphany of that sort of series of refutations of the Newtonian gravity came with the observations of the deflection of starlight around the limb of the sun, or distant starlight, where it clearly showed that the best prediction came from the general relativity. And this sort of sealed the coffin of Newtonian gravity. The reason we still learn about Newtonian gravity and the reason we still use Newtonian gravity is that Newtonian gravity can be explained to be a special case of general relativity. And that special case just happens to work best in and around the surface of the Earth or any other planet or shape with a high mass, where we don't move that much compared to the size of the planet. Alright? I hope that you have gained knowledge, found this I have told you about interesting. I find it very interesting. This is why I work with it. And I will continue to produce videos here on my channel to tell you about all sorts of things. Yeah. Thank you for listening.